Hello. So my name is Blerim, and this is a presentation of the Kuhn segment length concept. So first off, I'm going to give a quick introduction on just polymers in general. So polymers are essentially just really long molecular chains comprised of monomers, which is shown on the figure on the top left. So each monomer undergoes some polymerization reaction to form a long chain called a polymer. And an example here is given. These are just ethylene monomer units, and some polymerization reaction can occur, which gives us polyethylene. So some examples of polymers in real life, Teflon, which is a material that we use for cooking pans, rubber, plastics, of course, is a prominent plastic or polymer, polyester for our clothes, and then some also natural examples of polymers such as sugarcane, DNA, RNA, and wool. And the polymers can essentially be found in different molecular structures. So we can have a linear polymer, a branched polymer, which has side chains, and also cross-linked polymers, which are connected by those branchings, as well as a network polymer. And these different types of structures can specifically determine what type of application the polymer has and its purpose. So a quick introduction of the basics of structure of polymer coils. So the top left essentially just shows a random coiled polymer, and R in this representation is the distance from the origin, which has one end of the tail, to the other end of the tail. So R here represents the root mean square end-to-end distance. And we can have a formula for the R squared bracket 1 to the 1/2, which is just N to the 1/2 L. And N here is the number of monomer units. This is lowercase n. And L is the bond length. And this is a random coil representation. So this is ideal. There are factors that can affect the flexibility and mobility of polymer chains, making them deviate from completely random coil behavior. And one example is short-range steric interactions due to presence of side groups. This has an effect specifically in increasing the root mean square end-to-end distance, same as hybridization and bond angle effects. This also increases the root mean square end-to-end distance and makes the polymer coil more stiff, less mobile. And on the bottom right, we can see the difference between eclipsed conformations and staggered conformations. Staggered conformations are a little more energy favorable. You don't really want bulky side groups being right next to each other in the eclipsed conformation, as this increases the energy of the polymer. So the Kuhn segment length, the average length B of a number of segments N of polymer that behaves as a statistically random coil. So L is equal to capital N B. And so the root mean square end-to-end distance would be capital N B squared for homopolymer chains, where L is the total chain length. So essentially, we could use the Kuhn segment length to relate to the total chain length and also the root mean square end-to-end distance. So for flexible polymers, the Kuhn segment length varies from 6 to 12 monomer lengths. For example, polystyrene has a Kuhn segment length of 8 monomer lengths, while polymethyl methacrylate has Kuhn segment length of 6 monomer lengths. So we can see just from this comparison here that since polystyrene has a greater Kuhn segment length, it is a less flexible chain. And polymethyl methacrylate is a more flexible chain because it has a lower segment length. It is not a precise measurable, but it is more so a theoretical measurement to gauge the flexibility or mobility of a polymer chain. And the simple relationship here is it is related to flexibility. So a smaller Kuhn segment length leads to more flexible chain, while a larger Kuhn segment length leads to a less flexible chain. So it gives us a qualitative representation of flexibility, which is more qualitative. So how is it specifically measured? Theoretical measurements can be obtained. It is a theoretical measurement, but it can also be obtained from geometrical analysis of polymer chains using X-ray scattering or NMR spectroscopy, for example. So on the bottom left, one of these techniques can be used to determine the dihedral angle associated with a polymer chain. And so this essentially gives us a quantitative representation of the deviation from just straight behavior for a polymer chain. And this dihedral angle can be used in this equation specifically to get the root mean square end-to-end distance. And this root mean square end-to-end distance can be quantitatively related to the Kuhn segment length using the total polymer chain length. And then also the Kuhn length is 2 times the persistent length. And the persistent length essentially is the length that the polymer chain does not deviate from a straight behavior. So it is essentially the length that it is straight, and then once it makes some deviation at some angle, that is where the length measurement stops, and the Kuhn length is 2 times that persistence length. So there are multiple ways of quantitatively obtaining the Kuhn segment length. So why does it matter? Like we said, it represents the flexibility and mobility of a polymer chain. And on the left is one type of research paper that deals with the persistence length of cytoskeletal filaments using curvature distributions. And we can see that there's a big difference between the persistent length between the soft filament on the left and the stiffer filament on the right, comparing micrometers to millimeters actually. And on the right, this article actually dealt with exopolysaccharides produced by some bacterial strains, and they compared it on the viscosity of fermented milks. And using the Kuhn segment length between these exopolysaccharides, they viewed how these polymers and how stiff they were using the Kuhn segment length determined the viscosity of these fermented milks. So the Kuhn segment length definitely has some special applications in polymer uses. Thank you.